everyone, my name is Roxana and I'll be presenting our paper FactGenius, combining zero-shot prompting and fuzzy relation mining to improve fact verification with knowledge graphs. First, the task that we're addressing. We want to address fact verification that is given an input claim, which is a natural language sentence, and some evidence. We want to predict whether this claim is refuted or not. But we specifically wanted to focus on the task where this evidence is given in the form of knowledge graphs instead of textual documents. To address the task in this setting, we looked at the FactKG benchmark, which contains over 100,000 claims that are either supported or refuted by knowledge which is contained in the Wikipedia, a pretty large knowledge graph. Now, for those of you who are not familiar with knowledge graphs, you can think of them as, well, graphs that store knowledge, but they're more or less, this is a complete oversimplification, but you can think of them as labeled graphs. And when I'm talking about the nodes in these graphs, I'll be referring to them as entities. And then the edge labels, I'll refer to them as relations. But more or less, knowledge graphs should be containing knowledge that we as humans have of the world, and this should be a good source of information that can be used in fact verification. So this is why we were interested in this setting. And then there's this benchmark that was created for this. Now, this benchmark was mainly used in two ways. Claim-only setting, where we don't actually use the evidence, and the reason for approaching it in this way is to see whether the language models we use already have this information stored. But the more interesting setting, we would say, is the setting where we're actually trying to use the knowledge graph information in order to enhance the performance of the fact verification models. That's mainly what I'm going to be focusing on in the presentation. Now, this is the diagram of the system that we developed in order to address this problem. And we mainly have two components. Component called here the graph filtering component, which selects the part of the knowledge graph that is relevant to the input claim. Because these knowledge graphs can be very, very large, so we want to select a small subgraph that we can use for the particular example we're looking at. So that's the first component, the component that does this selection. And then we have a simple classifier that will just be taking in some textual input and predicting whether the claim is supported or not. And we can start with the first component, that component for retrieving the evidence or the subgraphs. And this component is mainly based on using LLMs in order to filter the relevant subgraphs. How do we do this? Well, we take the claim, and you have here an example of the claim. And for this claim, we select already some of the relevant parts of the graphs. And the way we do this is we take the entities in the claim. In fact, KG, these entities are actually given, but we could easily predict them based on the claim. And we also take the relations around those entities. In our paper, we only looked at the one-hop neighborhood. That means we took the direct neighbors of all the relevant entities. But we end up with this still pretty large list of relations. So that's pretty big subgraphs. So we want to filter these subgraphs. And to do that, what we did, we used LLMs. We prompted them, we gave them the claim, we gave them the relevant entities and relations, and we asked the LLMs to filter for us the relevant relations. So you can see the list gets much, much smaller. So this is now manageable to give as input to the classifier. Now, one problem that we had with the output from LLMs is that it might have been invalid. That means the LLMs might have hallucinated some slightly wrong relations that are actually not in the input graph, in this big knowledge graph. So in order to address this, what we did is fairly simple. We compared the generated output with the initial list, with the list that we gave here in a way. And when we did these comparisons, we used Levenstein distance, which we thresholded. And we did this validation in two different ways, which we called stage A and stage B. They're fairly similar, but for one of the stages, we looked separately at neighborhoods around entities, and in the other stage, we actually combined the neighborhoods of all the relevant entities when we were doing this matching. And you can see more details in the paper. Okay, now once we did this filtering of relations and we validated to make sure they exist in the graph, we have ended up with these subgraphs, which we simply turned into strings and we combined together with the claim, passed it to a classifier, and we got our prediction. And for the classifiers, we used three different versions. We used BERT and Roberta, but also a zero-shot LLM. Now for the results. In the paper, we have the claim-only results as well, but I'll focus here on the ones for with evidence. And there's two types of results we have for the setting where we are using the evidence. That is on a smaller version of DBpedia that is only with the relevant information for the benchmark, or on the full DBpedia. We compared with two of the approaches in the literature with the state-of-the-art approaches, and we broke down our results into different types of claims. We have two baselines that we used. A baseline where we actually don't use LLM based filtering, but we simply uh, compare with the claim with some simple model. And then baseline where we use LLM filtering. So the whole first component is exactly what I presented, but then we don't use these trained classifiers. We use some zero-shot classifier, and the performance for both of these systems is not that, or the claim-driven relation filtering or baseline actually performs a bit better than the state of the art, but the zero shot doesn't. Now, where we started seeing pretty good improvements was when we actually used BERT for the classifier, with a slightly better improvement for the stage B type of validation. And our best results were obtained when we used Roberta as a classifier, particularly with stage B validation, where we're actually maintaining more of the relevant connections. And the results are much, much better than existing state of the art. But these are results on this smaller version of DBpedia, not the full knowledge graph, but we are maintaining still very good results when we're considering the whole bigger graph, the whole DBpedia. So our best model, the Roberta classifier, together with the stage B validation, still performs much better than current state of the art. That's it about the results. You can see more in the paper. And as for next steps, We're considering expanding to other benchmarks, not necessarily fact verification, and also multi-hub neighborhoods for fact verification. Thank you so much. These are the resources you can check out.